Hi everybody, thanks for tuning in to this second video in transforming exponential functions, part 2, and I'm calling this one a strange coincidence that will show up here between a couple of these parameters. If you recall, in our last video we looked at the general structure of an exponential function, and there's all our different parameters there. A giving us the vertical stretch or compression factor, B is the base that is being exponentiated, and that's an important thing. We've got H for a horizontal shift and K for the vertical shift. And one of the things that we observed in the last video was that the horizontal asymptote, which is a feature of all exponential functions, is shown to you right there in the equation y equals k. Whatever that added or subtracted number is, that is in fact the horizontal asymptote. Okay, we also looked at the restrictions for b in the last video, and so that's just kind of all the different little things that came up in the last video. And again, that direct relationship between the vertical shift and the horizontal asymptote and the restrictions on the value of b. Well, in this video, what we're going to talk about is A and H, the vertical stretch or compression and the horizontal shift, and those two things together form what I am calling this strange coincidence. And this is the coincidence, folks. It's kind of interesting that a vertical stretch or a vertical compression of an exponential function is exactly the same, equal in every way, to a horizontal shift. I don't believe that's true for any other class of functions, at least as far as I know. This is the only group of functions where stretching the graph vertically or compressing it vertically does exactly the same thing as shifting it left or right. It's a very interesting little thing. Let's take a look at why that's true. All right, but first I want to remind you of a very familiar, at least I hope it's familiar, law of exponents. When you are multiplying two numbers of the same base with different exponents, you can simplify that to just the base raised to the power of the sum of the exponents. There you go. That's a very familiar law of exponents. Hopefully you won't have any trouble accepting the fact that I could write that equation the other way around. X to the a plus b equals x to the a times x to the b. It's kind of splitting it up like that. Okay, we'll keep that in mind for a second or two, and as we look at our first example of an exponential function that's got a horizontal shift. Okay, so we've looked at that. We've got an a value of 1, we've got a b value of 2. We don't have any vertical shift, k equals 0 in other words, but we do have this horizontal shift of h equals negative 3, and please observe that x plus 3 means h is negative 3, and that is a shift left of 3 units. Okay, so now, just to remind you about that law of exponents there, written in that way, you can see that our function sort of takes the form there of that x to the a plus b part of that law of exponents, 2 to the x plus 3. Well, it seems like then if I applied that rule of that law of exponents, I could rewrite 2 to the x plus 3 as 2 to the x times 2 to the third. That's certainly true. And of course 2 to the third just equals 8, so that just means that I've got 8 times 2 to the x, which means that my function 2 to the x plus 3 is equal to 8 times 2 to the x. So my horizontal shift left of 3 units, when I sort of think about that and how it applies to my graph, and a horizontal shift left of 3 units is exactly the same as a vertical stretch of a factor of 8. So I have a base of 2 being shifted left 3 units, and that gives me the same thing as a vertical stretch of 8. 2 to the third, in fact. It's not a coincidence, folks. So let's take a look at the graph of these two functions, and just if that's not enough to convince you that those really are the same, which it probably is, but I want to take a look at the graph anyway. Here's 2 to the x plus 3, which on the left, which is shift left of 3 units. On the right, you see 8 times 2 to the x. That is a vertical stretch of 8 units. And you can see that they have some points in common, don't they? They both have the same y-intercept, and they have some other points that are the same as well. So 2, negative 2 is the same on both graphs, and 1, 16 is the same on both graphs. All right, so let me just demonstrate this, go into this a little bit more deeply here and show you that if I graphed y equals 2 to the x over the left there, that is the untransformed 2 to the x, if you think about that as a shift left of 3 units, I just want to demonstrate that using kind of a little measuring stick of 3 units horizontally and just kind of applying that at different places, you can see that the graphs really are 3 units horizontally apart from each other. Okay, so that's kind of interesting, just a little demonstration of that horizontal shift. Whereas if I graphed 2 to the x over there on my right side where it's multiplied by 8, that should mean that all my y values are multiplied by 8. Well, yeah, that's exactly true. If I look at, kind of a point by point, there's my y-intercept of 1 on y equals 2 to the x, and that corresponds to a y-intercept of 8, 1 times 8, on the transformed function. The point 1, 2 is on my graph of 2 to the x, and that corresponds to 1/16 on my transformed graph. So again, multiplying the y coordinates by 8 to get the new y coordinate. One more where the point 2, 4 is on my graph of 2 to the x, and that would correspond to a y value of 32, but I think you're going to have to kind of just trust me there that it does in fact go through that point. You can do the math, of course, and verify it for yourself. Well, I hope I've convinced you now without a shadow of a doubt that a vertical stretch and a horizontal shift are in fact the same thing when we're talking about exponential functions. Very interesting little feature. All right, let's do a couple more examples to wrap this up. Here's one that's got a horizontal shift of +1, x minus 1. It's got a vertical shift of -2, and we've changed the base now from 2 to 3, which, as you'll see, doesn't really change it a whole lot. But so there's all those little things kind of spelled out there, and the first thing I want to do is graph my horizontal asymptote at y equals -2, and then if I just kind of for a moment took a look at y equals 3 to the x and how that would go through a couple of easy to identify points there, the y-intercept, and where x equals 1, my y value would be 3 there. If I just thought about my transformations, that is, I'm going to shift those points to the right 1 unit, that's my horizontal shift, and I'm going to shift them down 2 units. That gives me a really good picture of what that graph is going to look like, and that's really about all I had to think about there. Here's a picture of the graph using our friend the Desmos graphing app, a really great graphing tool. Just to verify there what that looks like. Let's do another example now. This one is going to have something different in it. I've got an a value of 2 and a base of 2, so it's 2 times 2 to the -x plus 3. So when I look at all those different things there, I've got an a of 2, b of 2, h of 0, my h value is 0, and I have a k value of 3, so that is shifted up 3 units. Now this -x, that's the first time we've seen that in any of these videos here. It's a very important little thing to bring out, and that is telling you folks that the graph is actually reflected across the y-axis. That negative exponent means that my base graph is reflected across the y-axis. We'll discuss why that's true in class. You may have an intuition about why that's true anyway, about negative exponents and what they mean for the base. Reciprocal. So anyway, that is a reflection across the y-axis, meaning that the graph is going to be a decreasing curve. So let's sketch in my y equals 3 for the horizontal asymptote there, and thinking about that reflection idea, that means my curve is going to look like that, okay, decreasing. And if I do one more little bit of work there, figuring out the y-intercept by putting in x equals 0, I get 5, and so there's a picture of my curve. And you don't really have to plot a whole bunch of points here if you're observing the asymptote, the basic ideas of what's going on here. And there's a picture using a different graphing tool called Quick Graph, also a very good graphing tool on that one there. Just to summarize everything there, I hope that was enough examples, but just to summarize everything, I want to kind of finish this video up here. So there's all of our parameters there about an exponential curve. I hope this is starting to make some sense. Of course, there's a lot more exploration, a lot more practice that you should do to be fully master these ideas. But you're on your way. So now go do some math.